Hi and welcome to this video where I'm going to be explaining about the structure, the bonding and the properties of covalent network solids. This is one of the types of solids which you need to be able to discuss for NCEA level 2 chemistry. Okay, so covalent network solids. These are very large structures consisting of billions and billions and billions of atoms, all connected by covalent bonds, which are very strong. So these are not discrete molecules or ionic compounds or anything like that. So it's all covalent bonding over very large numbers of particles. Now there are a large number of possible covalent network solids, but only 3 of those are assessed at this particular standard. So they are diamond, graphite, and quartz, which is sometimes called silica or silicon dioxide or SiO2. That's all the same stuff, just different names. So those 3, diamond, which is pure carbon, graphite, which is pure carbon, and silicon dioxide. Okay, so first off, diamond and quartz. Both of these have very similar structures. And you can kind of see a diagram of a section on the right-hand side there. So you've got this 3-dimensional network where every atom is atoms. Now, in the case of diamond, every carbon atom is bonded to 4 other carbon atoms via covalent bonding. And every one of those carbon atoms is bonded to 4 other carbon atoms, and so on and so forth, which leads you to a very large, very strong structure, which is one of the reasons why diamond is one of the hardest, well, is the hardest material known on Earth. Silicon dioxide is not quite as complex, where every silicon is bonded to 2 oxygens, and every oxygen is bonded to some silicons. So it's a ratio of silicon dioxide. It's not like 1 to 2, like a molecule. It's more like an ionic compound where you've got a ratio, but they're bonded by covalent bonds. Okay, so thinking about both diamond and quartz, they have very high melting and boiling points. So it's one of their properties. They're not soluble in water, they're very hard, and they do not conduct electricity. Okay, so those are the key properties. So you can see that the bonding is this 3-dimensional structure where you've got a lot of covalent bonds connecting a lot of atoms together. Graphite is quite a different structure, and graphite is a layered structure. So each carbon atom is bonded to 3 other carbon atoms. So it forms these sheets where you've got all these carbon hexagons bonded together. So you've got these flat sheets. Now, because carbon normally makes 4 bonds, but there are only 3 bonds in each of these sheets, each carbon atom has 1 spare electron, and these electrons form a layer of delocalized electrons which sit between the layers of graphite sheets. This has a really interesting effect on the properties. So what you end up with is this layered structure. So you've got a layer of carbon hexagons, then some delocalized electrons, then another layer of carbon atoms, then some delocalized electrons, then another layer. So it's like a lasagna of carbon atoms and delocalized electrons. Again, graphite has very high melting point, but it's very soft, so the layers can slide over each other. And in fact, graphite is often used as a very high temperature industrial lubricant. And the other thing that's really important with graphite is that it can conduct electricity. It's still not soluble in water though. Okay, so let's think about some of those properties for a moment. Some of them are generic across all of the covalent network solids, and some of them are variable. So first off, melting and boiling point is consistent across diamond, quartz, and graphite. They all have very high melting and boiling points. And the reason for that is that all of the atoms are connected to all of the other atoms by these very strong covalent bonds. Strong bonds require a lot of energy to break. That energy comes in the form of heat. So they tend to have very high melting and boiling points because it takes a lot of heat energy to break the large number of very strong covalent bonds. And the other thing that is consistent across them all is solubility, and particularly solubility in water, but actually solubility in non-polar solvents as well. So to dissolve, the particles in that solid have to be more attracted to each other than they are more attracted to the solvent than they are to each other. Now, because these are all covalently bonded, they have no attraction to water. There's no positive and negative parts, there's no charge separation, there's none of that. So there's no reason for them to dissolve in water. They're just not soluble in water. Now, electrical conductivity is a bit more interesting because graphite can conduct electricity while diamond and quartz can't. And the reason is that to conduct electricity, of course, we must have freely moving charged particles. In diamond and in quartz, in diamond we've got only carbon atoms covalently bonded, and in quartz we have silicon and oxygen atoms covalently bonded. None of those are charged particles, and none of them are able to freely move because they're all bonded in place with these strong covalent bonds. Graphite, however, has layers of covalently bonded atoms, but separating those layers are delocalized electrons. Those electrons obviously can carry charge, which is why graphite can conduct electricity. And the final property is hardness. Now, diamond and quartz are both very hard substances. On the Mohs scale of hardness, I think diamond is a 10 because it's the hardest substance, and quartz is around a 7 or an 8 from memory. That's because when you try and cut or break a chunk of diamond or quartz, and it is possible, you have to break all of the covalent bonds. And there are a lot of covalent bonds because it's a three-dimensional structure. So because you're breaking large numbers of covalent bonds, it requires a lot of effort, which makes these things very hard. Graphite, on the other hand, is very soft because you have these layers and sheets. And because you've got these delocalized valence electrons between the layers, it allows each layer to slide over each other, which allows graphite to be very soft. The sheets themselves are you can't break those particles apart, but because the sheets are separated from each other, they do slide over each other, so that provides that property. Okay, so that's a quick look at covalent network solids. I hope you found it useful, and I hope to see you again soon. Thanks, bye.